Okay, so we're all blown away by what AI can do these days. But what if I told you that under the surface, a lot of these super powerful models are actually kind of fragile? Today we're going to pop the hood and see how fixing an AI's internal health is really the secret to making them truly powerful and reliable.
Think of it like a supercar, right? It might look amazing on the outside, all shiny and perfect. But if the engine is unstable and clunky, it's not going to perform well for very long. Well, it's pretty much the same with AI. For all their incredible power, a lot of models are secretly wrestling with some really basic hidden flaws.
And these flaws really boil down to two big challenges we're going to unpack today. First, this internal shakiness called numerical instability. And second, the problem that just keeps getting bigger, literally, massive model sizes. So let's start with that instability thing.
So what on earth does it mean for an AI to wobble? Well, it all comes down to this idea of numerical stability. And believe me, it is absolutely critical if we want AI we can actually trust.
Basically, numerical stability is just a measure of how much a model freaks out over tiny changes to its input. A stable model is your best friend. You give it a picture of a cat, it says cat. You give it a slightly different picture of that same cat, and guess what? It still says cat. An unstable model, though, who knows? It might suddenly say dog or just spit out complete nonsense.
To measure this, researchers have a tool called the condition number. You can just think of it as a stability score for each little piece inside the AI. A perfect score is 1. That means it's rock solid. But as that number goes up, the model gets more and more fragile.
And this slide just lays it out perfectly. On the left, with a low condition number, you get what you want, a stable, robust model. It's predictable, it's reliable. But on the right, with a high number, the whole thing becomes unstable and fragile. It gets thrown off by the tiniest bit of noise, and that inconsistency is a total deal breaker for pretty much any real-world use.
So you might be wondering, why don't we just teach all our models to have a low condition number? Well, there's a little technical catch. The math behind the condition number is what you'd call discontinuous. That means it has all these sharp jumps and breaks, which makes it almost impossible for our standard AI training methods to handle it. It's kind of like trying to ski down a staircase. It's just not a smooth ride.
But what if you could smooth out that staircase? Well, some really clever research has found a way to do exactly that, creating a much smoother path for an AI to learn how to be stable.
And here's the key idea. They created this new tool called a regularizer. You can think of it like a penalty flag that gets thrown during the AI's training process. This little penalty gently nudges the model, encouraging it to build more stable internal parts, the kind with a low condition number, without having to deal with that jagged staircase problem head on.
And here is the proof, plain as day. Just look at this. The top row shows you the messy, noisy images we start with. Now, that middle row, that's a standard AI trying its best to clean them up and kind of failing. But then, look at the bottom row. This is the model trained with that new stability method. It reconstructs the numbers almost perfectly. Seriously, the difference is night and day.
And the data just backs this up beautifully. On this graph, just follow that dashed orange line. As they apply this new technique, you can see the condition number just plummets. That's a huge win for stability. Now, look at the blue line. That's the error rate. It barely even moves. This is the holy grail, the perfect trade-off. You get a much healthier, way more robust model for almost zero cost to its performance. Okay, so we've made our AI more stable. Fantastic. But it turns out that same core idea of building a healthier model from the inside also helps us solve our second big problem, the fact that AIs are just getting ridiculously big.
Yeah, this is the model bloat problem. The latest and greatest models have billions, sometimes even trillions of parameters. I mean, these things are absolute behemoths, and while they're super powerful, they are also crazy expensive to train and to run. It creates this huge barrier to ever getting them onto normal devices, like your phone or your laptop.
Which, of course, leads us to the million-dollar question for the future of AI. How in the world can we shrink these things down, make them more efficient, more accessible, without gutting them of all their amazing abilities?
Well, the answer, believe it or not, ties right back into our theme of building healthier models. By encouraging smoothness during training, we can create models that are not only more stable, but also way easier to shrink down.
And the process is just so elegant and simple. First, just like we saw before, you train the model with a penalty that encourages smoothness. Think of it as forcing the AI to keep its internal information nice and organized. Then second, you use this powerful math technique to scan through those organized parts, and it intelligently finds and throws out anything that's redundant. And the best part?
The smaller model you're left with works great right away. No expensive retraining needed. Let's see it in action. Here is an image of a butterfly that was recreated by an AI. The original full-size model has about 134,000 parameters. And as you can see, the quality is fantastic. This is our starting point.
And now here's the result after they compressed that smoothly trained model by almost half. We've literally cut the number of parameters down to just 68,000. And just look at the image. The drop in quality is, well, it's almost impossible to even see. That is a massive gain in efficiency for such a tiny trade-off.
So what's the big picture here? We've looked at two totally different problems, instability and model bloat, and it turns out there's a really powerful common thread that links their solutions. The big takeaway is this. By using these clever penalties, or regularization during training, we can build AI that is just fundamentally healthier. This shifts our focus from just chasing higher scores on a test to actually engineering models that have a strong, sound internal structure. And the result is AI that is more stable, more robust, and way more efficient.
Which leaves us with a really fascinating thought. For years, the story of AI has just been about getting bigger. Bigger models, more data. But maybe, just maybe, the next great leap forward in AI isn't going to come from making them bigger, but from finally making them smarter, healthier, and fundamentally better from the inside out.